Yeah.
You know Hong Kong, right?
Do my whole research for Chinese,
So how many cities in China?
my whole research, my whole research.
So how many cities do you know in China?
Did they say anything wrong?
Do you know Shenzhen?
379 average lab.
Office.
That's my office.
Your team.
Thank you for cleaning the board so clean, whoever the office. Yeah, really have to clean. So, so we know about Fourier transform and Fourier series. I guess we learn much about Fourier series now. And the important thing is to learn the exponential form. Omega naught is equal to 2 pi over t. T is a period. And 1 over t is also equal to the frequency. Say the frequency. So given the fact that omega naught is also equal to 2 pi frequency. I'm going to use F here because that might confuse this type over here. And so these are called time harmonic functions. Or sometimes we call Fourier time harmonic functions. Okay? So they go by various names, and this is called the Fourier coefficient. Okay? So the task that you have been given in the last few days and maybe for the next few lectures is to find f sub n. So does anybody remember the formula for f sub n? Very good, okay? Excellent. dt f of t e to the minus j n omega naught t. Okay, that is the formula for f sub n. So f of t can be of various forms. And if f of t is a simple form, then you can perform this integration in closed form. And in this course, I presume you don't have to do this numerically. And f of t is always given to you in a simple form. And you can do this integration analytically or in closed form. Okay? So there are lots of exercises and examples in the textbook on how to do this for various forms. Okay, are there any questions regarding this? Yes?
Fundamental frequencies, if you have a bunch of components of them, like if you have e to the j something plus something with a different frequency, if you have a ratio of those frequencies, you can tell that it's a fundamental frequency if the ratios are integers?
No. I think there was a form that was something like this. Cos of 3t plus cos of 5t plus cosine of 7t. Say this might be A1, A2, A3. And this is, say, a P of t. The question is, if this is a periodic function of t. It is because it shares a lowest common divider in terms of the frequencies. There are 3 frequencies here. Omega 1, omega 2, and omega 3. And there is an integer common divider among them. What is the integer?
1.
1, okay? All of them will be divided by 1. So if you look at this fundamental frequency, this thing is periodic. This is periodic when t goes to 2 pi, right? So this function is 2 pi periodic. But this is just 3 times faster than this one. Okay, but this one will still be 2 pi periodic. It just goes faster by 3 times. This one is 5 times faster than this one, so it is still 2 pi periodic. And this one is 7 times faster than this one. It goes around 7 times faster, but it's still 2 pi periodic. So all the 3 frequencies are 2 pi periodic, and they are not multiples of each other. 5 is not a multiple of 3, 7 is not a multiple of 5, and so on. But there is a common divisor among them, which is an integer value. If there's no such an integer value, then this function cannot be a periodic function. Okay, for instance, if I give you it goes here. Okay, if I give you a function p of t, which is cosine of pi t plus sine of 3t, there's no lowest common divisor between those 2 frequencies that is an integer. Okay, this one would go oscillatory at one frequency, this one would go oscillatory at another frequency. But they will never come to term with each other in terms of starting out the same place. They will never meet at the same place again, or meet at the same value again. Yes, you have a question, Aaron?
So if you have a periodic signal with a DC offset,
Yes.
I have to take some periodic, but when I was trying to follow one of the rules I found in one of the other lecture notes, it said that you should be able to divide omega 1 over omega 2 or vice versa and land inside the real domain, I guess, Q is what they called it.
Yes.
But that could turn into an integer over a 0.
You don't worry about the static term. If you can add a constant term here.
Right.
Don't worry about that, because that function is periodic, no
Right.
matter what period you choose it to be. A constant term can be termed a periodic function with undefined period. So you can say the period is t1, t2, t3. It doesn't matter. What you're worried most about is whether these are periodic with respect to each other, whether this part of the function will repeat itself after a certain period. Okay, so what you have is that if you have a constant term added to this is undefined in terms of its period. Its period can be anything, so don't worry about it. Just worry about if there's a common period between these two. There's no common period between these two, because there's no largest common divisor that is an integer. Okay, they will never meet up again if they start at the same value. Okay, yes?
The square root of 3 would be periodic.
Square root of 3? Oh yeah, that would make it non-periodic. Square root of 3 is a number. What kind of number do you call it? Square root of 3? Rational? It's not rational, it is irrational number. Irrational numbers can never be represented by a ratio of 2 integers. Okay, square root of 3 can never be represented by a ratio of 2 integers. So this is an irrational number because it can never be written that way. Pi also cannot be written as a ratio of 2 integers. And because of that, it can never have a lowest common divisor. Okay, those are called irrational numbers. Okay? Okay, so that is one rule that you have to learn. Another rule is about folding. When can you fold this integral over so that you can save time on your integration? There was a very good example that we had last time, which was the cosine of t magnitude, and that's the function of t. It looks something like this. So this is pi over 2, this is pi, this is minus pi over 2, and this is minus pi, okay? And instead of integrating from 0 to pi, where pi is the period of this signal, we can choose to integrate from minus pi over 2 to pi over 2. Why is that so? Because if you look at this part, okay, this part of the signal is exactly the same as this part of the signal. Okay? And if you were to pick a fundamental frequency for this, okay, you would do a Fourier series expansion where omega naught will be your fundamental frequency. The f of t is your function, and in order to find the coefficient, you multiply by 1 over t and integrate, and this is your f sub n. Okay? So what is the fundamental frequency that you should pick? Omega naught is 2 pi over t, which is, in this case, t is equal to pi is equal to 2. Okay? So you ask yourself, this function repeats itself every pi value, so must this function, all the Fourier harmonics, must repeat itself according to the period of this function. Okay? So if you look at this function now, just this part of the function, which is the Fourier harmonic, it repeats itself from here to here. The value of this function over here is also the value of this function over here. Okay? So when I integrate from here to here, having this function multiplied by this Fourier harmonic is the same as integrating from here to here, having this function multiplied by this Fourier harmonics, because this repeats itself. So I can, instead of integrating from 0 to t, I can integrate this from minus t over 2 to t over 2. That would work just as well. Okay, that would just work as well for the reason that this is also a periodic function. Whereas some of the suggestions that we had in the last lecture was just integrate from here to here and multiply by 2. Why is that wrong? Integrate from here to here and then multiply by 2 is wrong, because this part of the integration is not equal to this part of the integration. Why is that so? Why is this part of the integration not equal to this part of the integration? What causes them to be different?
The phase angle is different.
The phase is different, okay? This phase function from here to here is not the same as this phase function from here to here because of the wrong period, okay? This phase function from here to here is the same as this phase function from here to here, okay? Because it satisfies the high periodicity, okay? So you cannot just integrate from here to here and multiply by 2. You will get the wrong answer, okay? You have to study this to make sure that you're doing things correctly. And then there's another thing about stretching. If you have a function of t, if you change it to a function f a of t, okay? Say a function f of t looks something like this, a periodic function just to make life simpler, it has a period of t, okay? What would f t over 12 look like? Would it become a faster or a slower function? Would it be stretched or would it be compressed? It would be stretched, because if little t here is capital T, you have to make little t here 12 times capital T before you reach the same value. Okay, so you have to write this 12 times over. Maybe I put a dot, dot, dot over here, dot, dot, dot over here, and then 12t. Okay, before it repeats itself. So it goes down very slowly, and then it comes up here. It gets greatly stretched. So if A is less than 1, it implies stretching. Okay? However, if I make the factor A inside larger than 1, say if I plot f of 5t, or maybe not so big a number, just 3t. Okay? So if I were to repeat this plot for that figure over there, where would this point t be on that figure if I make f of 3t instead? It will repeat itself 3 times faster. So when t is t over 3, it repeats itself already. Something like that, right? It repeats itself 3 times faster. Can you see that? Okay, so if I tell you that the Fourier series expansion of f of t is equal to f sub n e to the minus j n omega naught t, n is to the minus infinity to infinity. So f of 3t would be what? It's very simple. You can actually just replace t with 3t on the right hand side. It would work. Okay, it would work. F sub n e to the j n omega naught 3t. Okay? So what you have effectively done is actually replace it with a new fundamental frequency. And you can think of this as a new summation f sub n e to the j n omega naught prime t, where omega naught prime is 3 times omega naught. So the frequency has increased by a factor of 3. The fundamental frequency has increased by a factor of 3. This is one way to look at it, is that you have rescaled the Fourier series expansion so that the fundamental frequency has increased by 3 times, or you just replace t with 3t, that will work just as well. Because this is a mathematical identity. Okay, this is a mathematical identity. I can replace 3t on the left-hand side as well as 3t on the right-hand side. And you can do that the same to the f divided by t over 12. Okay? DC term. What does the DC term mean? You do a Fourier series expansion, there's always the DC term. Say if you have this Fourier series expansion, which term is the DC term? N is equal to 0. Very good, okay. DC term f of 0, or n is equal to 0, okay. And you can do a sanity check, okay, to see if you have a function that has DC or no DC term. Does this function have a DC term? Can you just eyeball this function and tell me if it has a DC term? Yes. It has, right? DC term is the average value of the function. If you have a periodic function, okay, DC term is just the average value. Okay? Does this function have a DC term? It has, right? What about this? It has. It takes the average is non-zero. So if I give you another function that looks something like this. Dispense its time to be positive as much time as it's negative. Does this function have a DC term? No. Okay, so if I have a function like this, it implies that f of 0 is equal to 0. So you can just eyeball a function and do a sanity check. Okay, do a sanity check and check if it should have a DC term. If you work out your equation, f sub n, and you set n to 0, and it's non-zero, check if it's agreed, if it agrees with your intuition. Okay, if I ask you to find the Fourier series expansion of this very complicated looking function, you get an f sub n, and it's non-zero, you must be wrong. Do a sanity check. Okay? And you can actually eyeball this function without even doing any mathematics. Sometimes just by eyeballing it, you figure out where the DC term should be. Use it to check your f0. f0 equals what? Okay? To check your working. Okay, so the next thing I have to teach you is that if you have a time harmonic input to a linear time invariant system, what should be the output? That actually is very simple. Okay, very simple. So, if we have a linear time invariant system, we know that if we have a real-time signal, okay, and this linear time invariant system is described by the frequency response of h omega, or the transfer function h omega. What is the output? What should I substitute in there? H omega times e to the j omega t, right? And since this thing is going round and round in a circle in the complex plane, and this thing is also going round and round and round on the circle in the complex plane for all t, this is a mathematical symbol for all t. Okay? You can just remove the real operator. So you can just remove, this is irrelevant, since that two functions have to be equal to each other for all t. Okay, so you often would just have this thing, linear time invariant system, this thing coming in, and then whatever that comes up must be this thing. Okay, don't worry about taking its real part, because that must also be true. If its real part is true for all t. Okay? So this is also true for Fourier harmonics. If omega is n omega naught, we just replace this with n omega naught here. But what must we do here? If we have a Fourier harmonic coming in, where omega equals n omega naught, I know that it has to come out like a Fourier harmonic. What must I do to this transfer function or the frequency response? I will have to write this with omega equals n omega naught. Okay, simple as that. And then, now if you have a Fourier series coming in, and you have a function f of t which is not expandable in terms of a Fourier series. Okay, this is your input to this linear time invariant system. We apply the principle of linear superposition. We know how to do that term by term on the second picture. Okay, the bottom picture is just the sum of every terms that you can see in the second picture. But the principle of linear superposition holds true here, because we have a linear system. So we can do term by term and sum term by term. So on the output, what I have on the output here would be just y of t is equal to n equal to minus infinity to infinity. I work on the output term by term. Okay, each output should be multiplied by the correct frequency with the transfer function of the frequency response at the correct frequency times f sub n times e to the j n omega naught t. So that is the output. I do it term by term. I just sum over every term. I get the output. Is this clear? Is this obvious, or is it baffling? Is it confounding? What is it? Or is it simple? It's very simple to Georgie. Okay? It's a piece of cake, right? To Georgie. What is that?
Didn't we do something similar a couple of lectures ago? Yeah. It's the same idea.
They use this in one of the homeworks.
What is that?
They use this in the homework that's due today.
Oh, that's due today. Okay. But this is lecture 7. I'm supposed to give this lecture today. So how come you already have it done in your homework?
It happens.
It happens, right?
Because that's easy.
It's too easy,
It
right?
is easy.
That's easy.
Okay. so this is section 6.3.1. I'm supposed to lecture on that today, but then it's so easy that you don't even have to listen to my lecture. You can do the homework. So no trivia, right?
Well, we've been doing that the whole semester, so
Okay.
it's like
Because we have such a good teacher, we learn things. You know?
Okay, thank you very much.
If I get an A,
I have to see about that.
let's go ahead. Oh, I forgot.
So, you're on camera. So,
I'll just leave it there.
So let me ask you one question. If f of t is a real function, what do you know about the relationship between f of n and f of minus n? If f of t is a real function, we have derived this property before. What is the relationship between these two? They have to be conjugate pair. Okay, you can also write it this way if you want. The reason is, if this is real, okay, every pair of this complex function, every complex number that you find in this series has to have a conjugate pair. Okay, if this is something like this, its conjugate pair would be minus n, right? So in order for it to pair with another complex number that is its conjugate pair, f of minus n must be f of n conjugate. So they always pair up together, and all the functions will be real. Okay, this is a very important property of Fourier series expansion that you should know. Okay, they always occur in conjugate pair. Okay. Okay, then we want to prove certain thing that is not obvious to you, and maybe it will be a bit of fun, since it's not obvious, that if you want to find the time average power in the signal, is defined to be the signal square, integrate over time, and over one period. Okay. I want to show that this is something like f of n squared, n equals to minus infinity to infinity. Okay? Which means that if you know the Fourier coefficients, to find the power, the time average power in the circuit, or the function, you just need to sum this over all of them squared, or you can do this sum. Either way is fine. Let's see if this can be proven. Okay? Let's write f of t magnitude squared in terms of f of t times f complex conjugate t. Okay? If f of t is real, then that's not necessary. But if f of t is a complex function, then this is necessary. And then I write f of t in terms of its Fourier series. Okay? I write this in terms of its Fourier series. So this would be equal to n equals to minus infinity to infinity f of n e to the j n omega naught t, okay, times another sum, which is conjugated. So it's fn complex conjugation e to the minus j n omega naught t. But I better use a dummy variable that's different over here. Okay, I better call this n prime. So that I can mix the two summations together so that you don't get confused. Okay? I can mix the two summations together now. N is equal to minus infinity to infinity. N prime is equal to minus infinity to infinity. I bring them under one sum. Okay? And then what I have in the exponent is just n minus n prime omega naught t. Is what I have in the exponent now. I bring the two summations together. It's quite easy to do. Mix them together, but make sure that they have a different identity when you mix them together. One is indexed with n, the other one is indexed with n prime. Okay? Now I integrate I integrate both the left-hand side and the right-hand side. I integrate from 0 to t and divided by 1 over capital T. Okay? The left-hand side, I will get this power, average power. What would I get on the right-hand side? On the right-hand side, this is the only function of t that I have to integrate. Without even doing my integration, okay, when n equals n prime, what does it integrate to? What? When n equals n prime, that exponential function is just 1. So if I integrate from 0 to t, I get capital T, right? And then I divide by 1 over t, I just get back 1. Okay? When n is not equal to n prime, what does it integrate to? It integrates to 0 because it is an oscillatory function. This function has a real part and an imaginary part that is oscillatory. Both of them will integrate to 0. So I don't even have to do the work. I know that that function integrates to 0 when n equals not equal to n prime. It integrates to 1 when n equals n prime. Okay? So I could, after performing this integration, replace this part with delta n prime. That is called the Kronecker delta function. Okay? I could replace that with that. And then if I have a summation, a double summation over a Kronecker delta function, what does that come up to? Say if I have n prime, n is equal to minus infinity to infinity, n prime equal to minus infinity to infinity. Fn prime, complex conjugate, delta n prime. That's what I end up with at the final stage. What does this summation become? The inner summation, see if I were to do the inner summation first. I just have to set n prime to what? There's only one term that survives. Okay, Ashley, what do you think? The inner summation, what do I get? If I sum over n prime. Not sure. You're Liu Qinggao, right? Am I right? Okay. What do you think the inner summation should be?
It's the last part only equal to 1 and equal to 1.
It only is non-zero when n equals n prime. So if I sum over the inner summation, what do I get? Yes?
F sub n.
F sub n, very good, right? I can move the summation slightly over here if I want to, right? And then I get n prime equals minus infinity to infinity. And this is 1 when n equals n prime, is 0 otherwise. There's only one term in this summation. Okay, you're correct, so this becomes f sub n. I have a conjugation. Okay, so finally this one just becomes one summation left, because the inner summation just becomes that. I just have that. And what is this? You see, magnitude squared of f sub n, right? I just have that, and I have proven that this is equal to the left-hand side. Okay, so I have 1 over t, 0 to t dt of magnitude square of this equals that. Okay, the power can be computed either way, using the Fourier coefficients or using the function. Okay, the function. Is this clear? Yes?
So if this is measuring power, then what does f of t have to be measuring?
Both of them are equal to each other. I have proved this identity. Okay, I proved that if you have a power in the signal that you're interested in calculating,
Oh, so
you can calculate it this way, or you can calculate it that way. This also means power.
so f of t is like the instantaneous power function.
This is the power that you have learned in your course a while back, right? And this is like the time average power, and that power can be calculated using this method as well, okay? Now there's a concept that you might want to know here, which is the concept of power orthogonality, okay? What it says is that if I have a Fourier harmonic expansion, if I have a Fourier expansion of a signal, okay, if I have a signal f of t given with the Fourier series expansion, okay, it says that the power embedded in this signal is the sum of the power embedded in each individual signal. There's no cross terms. There's no cross terms. When you multiply this thing out, the cross terms all vanish. Okay? No cross terms. So it says that the power embedded in this signal is the power embedded in each individual signal. If I have only one Fourier harmonic alone, okay, if I have a signal with only one Fourier harmonic alone, what is the power is very simple. Okay. This is the power, and taking the right hand side is trivial. I just got that. If I have just one Fourier harmonic, this would be the power. Okay. It says that this identity still holds true when I have many Fourier harmonics superposed on top of each other. They don't interfere with each other. You can just add up the power term by term. This is the concept of power orthogonality. Okay, you see this concept here. Cross terms do not matter.